This is Dr. Nat. Okay, well, we've seen all the math tools that we needed. We've defined them, hopefully. So now we can have a closer look at Maxwell equations. Remember I told you I've given you all the tools that we needed? Well, I lied. Well, no, I didn't lie really, but I didn't give you everything you needed in order to understand all of this. But we do understand what this means. These are vectors. This is a dot product of vectors. This is a cross product. These are cross products of vectors. So we start to understand a few things here and there, but we're still missing a few things. Like, for instance, what this sign means. And what is this weird D thing? It's not a D really. It's a round D or something. So let's have a closer look at it and try to understand what this means. For that, we're going to talk about something called partial derivatives. So if we look at this animation here, we see that there is a 2D surface, and I make it move so that you understand, the shape roughly looks like a saddle a little bit. Okay, so and like a saddle, it has, you can see this kind of shape here, and if we use this line, red line here, and this blue dot, and we make this dot move according to only the x-axis, and we see what the derivative on this particular axis looks like, looking at the red line here, well, we have a pretty good idea of the overall shape of this 2D surface just looking at the x-axis, at this direction. Now, how do we do that? Well, what we need in order to do that is to describe the variation of this function. The surface is given by a function when only x varies. In other words, you keep y constant, and you just make the x vary and see what happens with the derivative of this particular function, which is now a one variable function. And that's what you get. You get the partial derivative of f relative to x, which is noted that way, partial derivative of f relative to x of a two variable function, the two variables being x and y. So in that case, y is considered as a constant, and you make x vary, and that gives you an idea of the variation of this particular 2D thing, but it could be 3D, it could be anything, like for instance, if you take a 3D function here, function of three variables, well, it's exactly the same thing. Let's take as an example the partial derivative of y. Well, what you do is you calculate the derivative of a function, of this function, with x and z being constant, and that will give you the partial derivative. So again, overall, what that means is that you make one of the parameter vary and see what happens, what kind of rate of change you get, just like regular derivatives. So it's pretty simple, and it's just a particular notation that you get there. Now, the other thing that's in the Maxwell equation is this weird symbol here called del. Actually, in French and many other languages, we also call it Nabla, because it's a Greek word for harp. And as you can see, there's some similarity, graphically between this symbol and an old harp instrument. So anyway, in fact, mathematically, this symbol represents the gradient of a function. So what is a gradient? Good question. Well, it's kind of a generalization of the derivatives, So we've just seen the partial derivatives. Well, the gradient is just a sort of a vector whose coordinates are just the partial derivatives of the function, So that's called a gradient. Basically, it gives you an idea of how a multivariable function evolves, over depending on different variables. So in fact, this is more like an operator. Okay, so you apply a partial derivative thing, but considering the way we write it here, we can also consider that as a vector, and we'll see that helps us define something called the divergence. And we define the divergence of a field as being the dot product of the gradient by the field itself, or vector, which is the same thing, because this field here is just a vector with variable functions here of x, y, and z. And if we apply, if you remember, the definition of the dot product was equal to that, but also was equal to the sum of the products of the coordinates. So if we apply that rule to the gradient as being the first vector and the field vector being the second vector, then we get the dot product of del by f is equal to d over dx fx plus d over dy fy plus d over dz fz, which is this, which is a number, of course, because the dot product gives you a scalar, a number. And so what do we call that a divergence? Well, if the result here is positive, what that means is that there is a change in the result here, which tends to expand things, tend to go out, and which is represented here like this. Like, for instance, if you have something that generates some energy, it will have a positive divergence. On the reverse, if it's negative, that means everything comes in but nothing comes out, So basically it becomes what we call a convergence as opposed to a divergence. And finally, if nothing happens, if like you have a magnetic, or a current or something that goes there, and whatever comes in goes out, then the divergence will be zero. So this thing gives you an idea of how we're going to use a divergence, being the dot product of the gradient by a vector field. Let's see the definition of this thing now, the cross product as opposed to the dot product. Well, we call that the curl of a vector, because you remember the cross product, there was some idea of rotation, thing like that. We're going to see in an example soon. But basically, what this is about is that you do a cross product between the gradient and the vector field. Now, if you remember, when we defined the cross product, we saw that the result, would have those coordinates. If you assume that, for instance, A is equal to AX, AY, AZ, and B is equal to BX, BY, BZ, then the cross product, which is a vector, will have these coordinates here. These coordinates as first one, second one, and third one. So if you apply this to the gradient and the field, well, what you get is the second coordinates of the first vector multiplied by the third coordinate of the second vector. So that's this by this. That gives you this part here that we put there. Okay, so that's partial of fz relative to dy minus the third coordinate of the first vector multiplied by the second coordinate of the second vector. So that's d over dz of fy. So that's what we do here. So that gives you the first coordinate of the curl. Okay, and using the same principle here, you get this result here. Now let's see how that's translated in an example. Okay, let's assume we have this field here. Okay, so we have a field. So remember the field. It's a set of points here. It's a two-dimension field, and in each point of the field you define some vectors. Okay. Now, if you have a close look at some areas of this field here, on the top, on the left, on the bottom, and on the right here, you can clearly see that there's, like here, for instance, there's kind of a clockwise rotation around this area here in the field, right? Here there's a counterclockwise, effect. And again here, clockwise and counterclockwise here. Now, if you look with a math simulation at what happens when you put particles in there and let them flow freely, but influenced by those vectors here in the field, then you can clearly see, you know, the movements of the particle and see, although it looks complex like this, it actually defines pretty clearly and precisely what's going on, you know, when you put a fluid in that field. So that's pretty interesting. Now let's look how it's connected to the curl of that vector field. Okay, so let's stop like this. Okay, so here we can see that field again, except of being vertical, it's horizontal. But basically you can see it as a slice of a 3D you know, volume. You know, it's just one slice, and you can have it on any z plane like that. So if you look at this, and you can see the four areas here, you know, that we saw previously, and you try to draw the curl of that vector field here, you can see that the vectors here, for instance, are higher, which means the rotation effect is stronger, and also the fact that the vectors are directed that way, of course, gives you the axis of rotation, if you remember, you know, the definition of cross product. But also it will tell you that in that case the rotation will be counterclockwise here. Here, for instance, on the front, which was the bottom before, you can see there are negative here, which means actually the rotation will be that way. Okay, so by looking at the curl, you know, from a math perspective, you have a pretty good idea of what's going on in a fairly complex environment. So that's pretty cool, actually. So now we have everything, finally. You know, we understand what this means. This means the divergence of an electric field. This means the curl of an electric field. But anyway, so very quickly, you know, this first thing here, well, the only thing missing is, well, epsilon zero, or epsilon naught, as you call it. I don't know why, you know, this is a zero, this is not a naught, this is a zero. But anyway, epsilon naught is just a constant that's there to make sure you have the right units, you know, to be compatible here, to be able to say this is equal. So don't worry too much about it. We'll talk about it in a moment, but for now it's not very important. It's just a constant. Rho, you know, which is a Greek letter, is here more meaningful. It's actually supposed to give you an idea on the charge density, which basically is a number of charged particles per volume unit. And so what that says is the more you have charged particles, and the more divergence you will have of an electric field, which makes sense. You know, the more charged particle you have, the more electricity you will produce. Basically, that's what it says. So you might think it would be the same for magnetic field, but it's not. And why is that? Well, if you look at the, you know, this drawing of one of the first drawing made, and that was showing a field, actually, a magnetic field based on a magnet. You know, that some guy just threw some iron dust near a magnet, and this is what happened. And here we can clearly see, you know, that it goes from the magnet back to the magnet, you know, all the time. There's nothing that goes out. Well, you could think it would be the case here, but in fact these lines here come back there, here. Okay, so what that means, what this equation means, is that nothing comes in, nothing comes out. You know, everything that's produced by this volume comes back to this volume. That's what that means. Now this one is more interesting, actually. This one says, well, if I make a magnetic field vary over time, you know, yeah, well then it will be proportional to the electric field here. So in other words, if I make a magnetic field vary, it will create an electric field with some, you know, direction, etc., based on this here. And we put a minus sign here because in fact this electric field, if you put a conductor in this electric field, it will generate a current which itself will regenerate a magnetic field which will tend to fight against this one, you know. But that's the idea. So this is actually how electric generators work. Yeah, you know, you put some fuel in an engine which has magnet, and you make that engine, you know, turn and make varying field because of the magnets. That will generate electricity. Yeah. And this is kind of the reverse, but it's a bit more tricky, as you can see. Well, the first part of it is very similar. It says when there is a, you know, a conductor with some current flowing in it, that will generate a magnetic field. Okay, and actually it was this was discovered and expressed by a French physicist. Yes, called Ampere. Okay. And also give his name to the unit of current, you know, so a pretty big guy, smart, yeah, smarter than me. But anyway, this guy was able to derive that and say, well, when there is a, you know, current density here, that will generate some magnetic field, and that's how, you know, engine works too. You give some current and it will generate a magnetic field which will move magnets, and then you get an engine. Yes, you know. But Maxwell said, yeah, okay, that's good, you know, not bad for a French guy, but actually you don't take into consideration another case where you actually cut the conductor and you put two metal plates in between here with some space, empty space, which means that the current cannot flow, you know, from one side of the place to the other. And you would still see a magnetic field if you make the electric field vary, if you make the electric current vary, and therefore the electric field vary. Well, finally, you know, we understand Maxwell and Maxwell equations. So, you know, let's celebrate. To you, Maxwell. But now that we understand Maxwell's equations, it's time to use them. Okay, and that will take us to our last step before the Grail, you know, the Bell's equation. And this last step is called Malus law. Malus, another French guy. So we'll see that in the next video. It's gonna be so exciting. See you then.